But let's start with today's seminar, and it gives me great pleasure to introduce today's speaker, who has flown all the way from the US to come to us and present to us on this exciting topic. Unfortunately, COVID has made it necessary to change plans ad hoc, and so unfortunately, Professor Elise is currently confined to a hotel room, but as Tesco alerted to, hopefully she will be able to be around at ITLS and another place in Sydney during the rest of her stay here in Australia. And before I continue with the formal introduction of Elise, I would like to acknowledge the traditional owners of Australia and recognize their continuing connection to land, water and culture. I'm currently on the land of the Gadigal people of the Eora Nation and pay my respects to the elders past, present and emerging. I further acknowledge the traditional owners of the country on which you are and pay respects to their elders past, present and future. As we now move to online, as in the past, please keep yourself muted. We will have a 40 minutes presentation, which will be followed by an opportunity to ask questions. So there's a 20-minute Q&A part of this seminar as well. So today's presenter is well established and is internationally well known, as we have seen in the discussion just now. And Professor Elise Miller-Hooks holds the Bill and Eleanor Hazel Endowed Chair in Infrastructure Engineering and is the interim department chair of the Sid and Reva Dewberry Department of Civil Environmental and Infrastructure Engineering at George Mason University in the US. She's also an advisor to the World Bank Group and the founding editor-in-chief of Elsevier's Sustainability Analytics and Modeling Journal. She has experience in disruption planning and response, multi-hazard civil infrastructure resilience, qualification and protection, stochastic and dynamic network algorithms, transport systems engineering, intermodal passenger and freight transport, real-time routing and fleet management, including paratransit, ride-sharing, bike-sharing, delivery, hospital capacity planning for research, and collaborative and multi-objective decision planning. So we a very broad set of interests and really a well-versed expert. I'm really happy to have her with us today to present to us on the optimization and machine learning in urban transportation under a sharing economy. So without any further ado, Elise, thank you again for making all the way to come to us, and hopefully we will see each other face to face later in the week. But for now, the floor is yours. Thank you.
Thank you so much, Rico. And I thank ITLS for having me out and inviting me to give this talk. I really do wish I could be there live with everyone. And I do invite everyone to feel comfortable to reach out to me through email or otherwise. And I'd be happy to talk offline to whoever would be interested. So I will be talking today about the sharing economy. And I want to start by saying that I'm not in any way suggesting that I know everything about the sharing economy. This is new and it's a new way of thinking, but I asked the question, is it really new? And what makes it new? And where have we all been contributing, and where, in what ways do we contribute, and have we been contributing to the same idea? So I'm going to sort of open more questions that I'll probably answer with this talk, but I hope that it will open our minds and get us thinking. Okay, sorry, my thing wasn't moving. Okay, so I need to move this down somewhere. There's a little bar here that is blocking some of my screen, so I'll have to be moving it around.
We can see it well.
So the first thing I did was I asked, well, what is the sharing economy? And is it really different from whatever we've been doing? So, well, it's the sharing of excess capacity. And so we think about, well, we rent a room or a carpool, and these things go back for, hundreds of years. People have been renting rooms at people's houses. So that's not new. But, well, what is new about it? Well, we could say it's facilitated by peer-to-peer exchange. And that's true, but is it really that different? Maybe not. Think about a bulletin board where you could put your room for rent on the bulletin board and somebody sees it. So what are we doing? We're replacing the bulletin board with a digital bulletin board. So that's not so, interesting, what I was thinking. But what are we doing? Well, we're doing this at scale. And I think that's where the novelty comes. So I started looking at, well, what are we, what are people saying about that sharing economy? And some have mentioned it also as collaborative economy, where we're combining our assets. We have things, we have skills, we can combine them to do certain things. I even saw something about shared jobs, which had not crossed my purview before. So the Harvard Business Review in 2015 argued that sharing is a form of social exchange that takes place among people known to each other without any profit. Well, if we look at the sharing economy that we all are seeing today, I don't think that without any profit part really applies. And they said when sharing is market mediated, consumers are paying to access someone else's goods or services for a particular period of time. And this is really an economic exchange. So are we really talking about sharing economy or are we really talking about an economic exchange? Don't know. I mean, there's arguments to say that we're really talking about an economic exchange. Also later in the year 2015, Knowledge is some kind of news item from the Wharton School of Business. They talked about sharing as the use of technology to reduce costs and enable customers and freelance workers to do business. So it is a way of flipping our thinking. It's buying mobility rather than buying a car. It's, I don't need a drill, I need a hole in the wall. And I really like that way of thinking because transportation, most of our careers, we're trying to minimize the amount of time people are spending in transport modes and getting them to have, shorter vehicle miles traveled. There's not a lot of careers that you try to, minimize how much of that. I don't know why my key isn't working. Okay. So I wanted to take a way of looking at the work that my group has done over the years and try to think about, well, how is this the sharing economy and how does it contribute? And at the end, I invite everyone to think about their own work and the work that they're doing, that you all are doing, whether it's academic or in the field, to think, okay, am I contributing to that sharing economy and in what way? And one lens that I can put on that is coming from the healthcare work that I do in hospitals. So I work on surge demand for hospital, trying to understand the surge capacity of hospitals under surge demand. And in working on hospitals, we talk about the services in terms of staff, stuff, and space. So you can't have service if you don't have all of these things. And so we think about the staff are the workers, the stuff is the equipment. I was thinking here, if we now put this in the transportation area, we would think about it in terms of the stuff is cars and the space would be like location, like parking spaces. And as excess capacity decreases, our need for greater efficiencies for utilization increase, and the more we have to look at where are the shortcomings in our system, where is this, are things tight? And so we might find that in space, but we might also find that in the staff or the stuff. And you cannot have services without all three. So online, we can use optimization and machine learning to facilitate new transport markets and services, new mechanisms for existing services like microtransit services that I'll mention. And offline, we can inform urban transport planning and policy. I'm going to talk today about 4 areas: vehicle sharing with bicycles and cars, ride sharing in terms of parking, ride sharing in terms of paratransit, airport shuttles, and microtransit. Again, I've got to move this little bar around. Parking in terms of pricing and new markets, and delivery. I'll be talking about meal delivery and same-day delivery. All right, so back in around 2007 to 2010, a student I had working in my group and I worked on vehicle sharing systems, and we put out a series of papers. This was early in that work. At the time, Velib was the big sharing system in Paris, and there weren't too many other very successful examples of bike sharing or car sharing. What we still believed in it at the time. It was, quite early in that area. but it was already out there, but it was not an area of, intense research at that time. So we asked, well, how do we design these systems so that they can support transit? And so this picture is showing you a transit line, a mass transit line. We had a train, an underground train. And then
Elise, your
yeah.
slides are not progressing. It's still on sharing economy.
Uh-oh. Okay, you know what? I feel like something's wrong because my click, okay, that's really not right. Okay, let me try sharing. Actually, maybe what I'll do is I'll stop it. And let me try sharing again. I thought something might be wrong because it's not moving with the button, the right button. I am not sure. Okay, let me try this. Is that working?
That looks good.
Yes.
Okay, now let me turn, wait, this bar just keeps going in the middle for some reason. I can't get it to go elsewhere.
We can't see the bar though. We can't see it.
Okay, that's good. It's right in the middle of the words. Is it moving now?
Yeah.
Okay,
yes.
Sorry about that. Okay, so I just talked about the sharing economy and then the need for sharing efficiencies, and the 4 areas I'll be talking about: the vehicle sharing, the ride sharing, and the parking and delivery. So beginning with the vehicle sharing. So this is a picture of the Washington, D.C. bike sharing system back in the 2000s. And so this was the system that we were looking at, the idea of extending the reach of the metro system with the bike sharing facilities in place. We designed a bi-level network design problem to model the system. And in the bi-level program, the idea is we have an upper level where we're taking decisions about where to build our stations, what capacity to have for these stations, and what their base inventories should be. And then later, we ended up working with Washington, D.C. on items related to expanding their system at the time. Since then, it's been expanded, and then they scrapped it, and they've done a whole new system. But at that time, we were talking about trying to expand the system they had in place. They were very concerned about transit equity across the wards. So DC is divided into wards. They're not economically even, and they wanted to make sure that every ward had something, even if they weren't going to have a lot of flow. And some other site requirements we had to incorporate that we hadn't thought about when we were thinking about it more mathematically, such as that amount of sidewalk space you have near a metro station, for example. So you have this upper level that's making these decisions, and then you have the response of the lower level users, and your goal is to come up with an equilibrium solution between the levels, which gives you the best you can do in terms of your design, given the way users will use the system to their own advantage. So we came up with that. Oh, it's not moving forward again. Oh, I've never had this problem before. This is a problem. Can you see that it's moving forward now?
Yes.
Okay, I don't know why it's getting stuck. Okay, so we applied this. We had an exact solution technique, and then for a simpler version of it, we had a hybrid approach where we decoupled the upper level and lower level. We used exact solution for the lower level to create the fitness values for the chromosomes of the upper level decisions, and ended up with a hybrid GA. So we've implemented both of these, but for the large real world problem, we could not back in the 2000s implement the exact solution approach. So we applied it, and you can see in the picture that it picked 19 of the 100 metro stations, plus a whole lot of other little dots there to position the bicycle sharing system at, and it told us all the things that we should be doing. And in the end, the application showed that a close coupling of these two could really affect and provide a better public transit service. We also looked at fleet management for the vehicle sharing systems, and I love this problem because it shows something really interesting that's mathematically quite difficult, but really important. So here, this work, we said, well, how do we redistribute the bicycles to ensure that there's a really high probability that when somebody shows up, they get what they need? And there's, either they're going to want to check in a bicycle or car, or they're going to want to check out one. So there's a duality between the spaces and the vehicles. The more vehicles you have, the fewer spaces you have, and vice versa. So as a result, we end up with a stochastic mixed integer program with joint chance constraints. which is, an interesting problem difficult to solve, but really, really important for looking at this problem. It's a very unique aspect of this problem class in, having this duality between these. We developed a p-efficient point generation technique that's exact, that was very complicated. And then we made an assumption of independence across stations, and we were able to do a cone generation approach that was quite fast comparatively. And we applied it back then on the Singapore car sharing network. We had data from it. And what's interesting is that Singapore car sharing system failed in around 2004. And this is around 2008 when we were doing this work. So at the time, this was just not, so successful. But we looked at it using their data, and we showed the fleet management strategies could account for the stochasticity. And then by doing that, we were able to have a much better, a more reliable system than when we use static methods. We did a lot in the ride sharing world and are continuing to do some work in this area, but I hadn't thought of it as a sharing economy. I just thought of it as a service that we need to, give to people. So we had a number of projects related to paratransit, and we worked with a company on this that ran a paratransit company. So here, the idea is you have in the US, we have to supply transit to all users, and those who cannot access public transit need to have it provided to them in a door-to-door way. And we want them to share the rides so that it's not as expensive to operate. So the idea is if you had a taxi, you have a pickup, drop off, you have another pickup, another drop off, but you don't have somebody sitting in the vehicle at the same time as doing another pickup. In a ride sharing situation, you can pick up another one, and you can have, end up dragging people around to a lot of different stops. And that's a way of trying to get, more efficiency out of your runs. But there's then a lot of different constraints we have to put on that. So for example, we can have a maximum ride time per passenger. You can't have somebody dragging around all day long. We had like no idling when passengers were on board, and we had specific time windows for drop off and pickup. And these were required by law. So if the contract was not met, then the company would be fined. And ultimately, if they didn't, they had enough of these fines, they wouldn't get a new contract when it was renewed. So it's very important to them to not, mess up and miss time windows and so on. We used a method called parallel insertion method, developed in the 1980s, and we, sort of expanded on this very simple method, and it worked extremely well. The company has a system called MRMS. They embedded it within the MRMS system. They used it for their own facilities, and they used it, and other companies have used it across the US. I don't know what's happened since. It's been a while since I talked with them. And the goal really is to squeeze out the idle time. As you see on this little picture on the right, that red is the idle time. The vehicles are sitting and doing nothing, and we really want the vehicles to be operating. We want to have as few vehicles operating as possible, but still meet all those deadlines. So at the time, we had 2 dispatchers working together 6 hours every night, and they would work on 450 requests for the following day. They would take 55 minutes for us to do a run, and 7 minutes to find our first feasible solution. So we compare that to what they were doing, and we found that in that less than an hour of runs, we could get a reduction in the number of routes by almost 13%, and we could save about 22% in vehicle kilometers traveled. This led to approximately $800,000 US in annual savings, and this is at about $2010, $2011. So for this smaller company, this was a really big deal. It saved them, all kinds of money, and plus, not to mention that they wouldn't have to pay these people to sit all night and do this by hand. And it also made it possible to digitize the whole thing and not have the drivers have to come in the morning and go pick up their rosters. They were able to now just get it to their little device. This was so successful that we work with them on a dynamic version of the problem. I won't spend much time on that. We didn't spend a lot of time with them on this. We did get pretty far, and then I'll share with you that we had a change in scope due to a new contract that they had come in, and I'll share that with you in a moment. But basically the idea was to take between 10 and 50% of our calls and assume that they were will calls. They came in dynamically, and to see how we could serve the dynamic calls and if we could do that more efficiently. And we were able to do that quite well using a rolling horizon framework version of the same heuristic that we had used for the earlier static approach. We recognized as this was rolled out that there were issues of dealing with uncertainty. So once you try to use these things in reality, the reality has a lot of new things that pop up, and including, a lack of reliability in the exact knowledge of travel times. So we had to look at how to deal with issues of late penalties. If there was uncertainty and they came too late because they just didn't know to plan for it, they would start getting those fees charged, and they were very concerned about that. So the operators started changing things around themselves. They started adding slack to the schedules. They started overestimating travel times, over tightening time windows, to try to force the system to give a little more slack so that if they messed up, they would still be on time. We did some experiments in a simulated environment to see how often we might expect to violate those time windows. And we found that greater than 12% of the customers' time windows were violated, often by more than 20 minutes. And by doing this idea of tightening the time windows, their costs went up a lot. So there's this trade-off, right, between the costs and how much slack to put in. We also found that out of 1,000 simulation runs, 35% of customers were picked up late in more than 100 of the runs. So that's a lot. That's a lot of issue, right, to have in reality. So we wanted to think about it, and again, it's not moving forward. There we go. We wanted to think about this reality of dealing with uncertainty. And so we started thinking about using taxis as recourse. So this company also owns a taxi company called Regency Taxi, which you'll see in the DC area. The idea was that if I knew that my vehicle was operating and was possibly going to be late, I could call a taxi. And then the taxi would take care of it. The issue is that if the taxi is called too early, then you would have made it, and now your costs are really high for operating this. On the other hand, you call the taxi late because you want to wait out as long as you can to see if you might make it. The taxi could also be late, and you'll be paying both fees. So the question is when to call that taxi. We looked at some methods that are just simple, like a threshold policy. Call it whenever there's probability that you'll be late is over some threshold, or the expectation is greater, that it'll be late than if the expected cost of the taxi pickup. So we would compare these things, and we tried this, and we had some luck doing that, but we wanted to make this a more formal problem. So we investigated this problem we call taxi as recourse problem by considering the specifics of the lost opportunities when we decide to call the taxi. So the idea is that you have your system, it's operating, you have your paratransit system, vehicle going out, it's real, the travel times are being realized, you're learning as you realize them, and then you gain from postponing your decision. You gain knowledge into the future about what's going to happen. And so there's this hidden opportunity for later decision-making. And the question of when to stop, when to make that decision to call that taxi is the optimization problem. And this we modeled as an optimal stopping problem. This is a problem that is used in real options in the stock markets. And it's used for all kinds of interesting problems, like when should you replace your hip, things like this. And so we modeled it this way. It's a very difficult mathematical problem. And ultimately, we also had to model the taxi itself with some randomness. So we have both of those vying against each other. We came up with the proofs of how the optimal stopping set looks, the idea that there's a continuation in a stopping region with a single line between them. So there's a continuation region that lies completely above the stopping region, and it doesn't look like this on the left. And then we also showed a myopic version of this where we don't account for those future opportunities for learning in the stochastics. And we used a binomial lattice method for solving this. So as I mentioned, we were in the middle of working on this dynamic version and that's where we thought we were going to be working. And we were at a meeting with the company when the company learned that they had won a new contract to be Supreme Airport Shuttle. So they have now a new airport shuttle system. And at the time, they didn't know how they should operate it. And so they asked us to change course and focus on the operations of the airport shuttle system. So if you go into Dulles or National in the Washington, D.C. area, you'll see Supreme Airport Shuttle, and that's what I'm talking about. So in short, I'll just say that they asked us to look at 3 different policies. That was to separate the outbound and inbound trips, to do inbound after outbound, or to let them just go together. And we said to them, look, policy 2 is always going to be best, because if it's best to do inbound after outbound, then policy 2 will pick that because it has the most freedom. And in fact, that is what we were able to show, is by leaving the freedom to the optimization, we were able to reduce the number of vehicles and the total cost to them. And that was the policy we recommended. We also, for that case, developed a column generation and set partitioning based approach and a pin variance, that heuristic that I mentioned earlier. While we were working on this, we saw that Hurricane Sandy had come in and had done a lot of damage in the northeast of the US. And we had started thinking just offline, my students and I, about evacuation of the mobility impaired. And just as a side thing, we did a little investigation into the use of the paratransit relationships to aid mobility impaired persons in hurricanes. And so we did a joint location, routing, and a shelter kind of problem. So it was the idea of using these vehicles and the drivers who know these clients to go out, try to get these people who cannot access public transit and cannot drive, pick them up and bring them to a subset of the shelters that would be set up for their needs. And we developed a methodology for solving this that we then applied for New York City area, and this is just some results from that. And I just wanted to share that as a thought about the use of these systems to help the mobility impaired. Very recently, we worked on microtransit, where the idea is that you have this flexible, dynamic system for offering transit services. So the routes are generated dynamically, but they're subject to staying within a zone. So these are public system offerings, and the idea of offering them in an area affects, transit really affects the vibrancy of an area. And so it's really important that if you're going as a city to choose where to try to operate these very nice systems, that it be chosen to improve equity. And so we made equity a core focus of the transit design, the microtransit designs problem, where we're looking at how do we decide what particular traffic analysis zones end up inside each of the zones. So we have a preset number of zones. We can't cover the entire area. Where exactly do we put these zones? And we developed a solution methodology based on taboo search and mathematical models to solve this problem. I think what's interesting here is that we showed that there are different ways to look at equity and thought about both vertical and horizontal equity. Vertical equity comes about from looking at demographics, and horizontal equity from more about proximity and access. And again, Washington, D.C. area, and you can see how different the zones come out when we look at different objectives. Even though we're trying to look at the equity issue, it could be that we actually don't come up with the most equitable solution if we look at only one type of equity versus another. And we found that by looking at both vertical and horizontal together, we did the best for truly enhancing equity. Next, I want to talk about parking. So I had this idea that individuals, and actually a colleague of mine brought this up to me, and then we started thinking about this, that people are sitting on excess capacity. So if you have a home and you have a parking spot, maybe even, let's say I lived in the building I'm in now in Sydney, and I had a parking space and I were to work somewhere and take my car out for the day, that I would have this space that's empty, and somebody coming into this CBD might want to use that space. And that's a way to not have to build more space for parking. So the idea that individuals could enter the parking market in that way. So we wanted to come up with a way of crowdsourcing the parking market. And here we looked at event-based parking. And what can I say about it? We have elastic demand. So if you price things too high, you're not going to keep the demand. So you want to be very careful to, have the prices be decent at the same time as you want, as individuals or different parking garages, you're competing to try to get the most revenue. So the higher you charge, the fewer people will come, but ultimately there's that point where you'll get the most total profit. So we have modeled this as a multi-leader, multi-follower problem. It comes out as a stochastic equilibrium problem with equilibrium constraints, and I'll show you that here. So the idea is that you have different owners of the parking. They could be individual owners, they could be a group of individuals, or they can be a garage owner, and they're all competing. The thing is that they're competing, but they share the lower level. That lower level is the parking market. And so they're competing with the shared market at the bottom, and in an environment where the demand is uncertain. And so we can solve this problem through a diagonalization approach that we've used, and a sample average approximation that we applied. And we were able to get solutions and show that this worked pretty well. We were able to show that adding private parking led to about a 7%, on the order of about 7% of the market. We had 1,700 public parking spaces and 130 private individual spaces. That this increased social welfare with more crowdsourced spaces. We had an average price drop for everyone of 15%, but the users served increased by 7%. We had a revenue of public locations that decreased by 5%. And we found that if we ignore the uncertainty and use the expected value, that the revenue reduced for everybody. We also tried things on competition. What if we had no competition? In that case, the total revenue of parking market went up, but the consumer surplus went down quite a bit. And so we found that, that competition can actually really help the market. And you can see that in the table. I don't know why sometimes it gives me trouble. We also finished work on dynamic pricing for parking in non-event kinds of situations. In this case, we looked at a smart parking system where we have real-time monitoring of the parking spaces and the prices that are on the market. We have competitors, and the idea is to have them each operating in this real-time environment, each as its own agent, and everyone trying to maximize their own profit. So they could be individuals or they could be companies that own their whole parking garage. We developed an agent-based model of the environment for obtaining the observations. So, we used a multi-agent deep reinforcement learning approach to estimate those prices. And so here, the idea is that we don't know much about the uncertainty. We're going to just have it be sort of revealed to us in some ways in a data-driven approach. This approach uses a queue function for each owner agent that's updated at each decision epoch, and it learns from the observations from that agent-based model of reality, because we don't have real reality to test this in. And we use a temporal difference or TD algorithm to learn the queue functions. So here, oops, sorry, I'm struggling with this thing on my screen because I have a small screen. I don't have a lot of space to move this bar. So the results of the multi-agent setting compared to the single agent setting showed that an average improvement of 26% in total reward for using that multi-agent setting. We tried some things with looking at a fully cooperative versus a partially competitive environment, and we found that by incorporating some competition, we actually improve things for everyone, and the total market wins out. And And I think that's all I'll share with you on that one. If I can forward. So last, I'd like to talk about delivery. So I think everybody has become more familiar with online delivery. I certainly have become better at that since COVID came. We were estimating long ago that that there would be a very big online delivery market. But once COVID came, the things we were targeting were just blown away, and the numbers are just enormous now. So this is a really big market. Yeah, I don't know why. There we go. So I started in my group, we started working with Grubhub. They are a company like Uber Eats. They deliver food within, I guess, many countries, but I know the US operations. And so here you have customers, you have restaurants, and you have delivery vehicles. And the delivery vehicles are crowdsourced drivers. They come into the system for about 2 hours at a clip, and they check back out. And they're looking for opportunities that look good to them. They position themselves so that they can get the most good, high-paying delivery opportunities, and they have the opportunity to turn anything down they don't want to serve. So we started looking at this at the beginning of COVID, and we were thinking then about how to keep these drivers far away from each other, because it became so crowded that we thought, wow, we're endangering these young people who have stepped up and we're starting to do the deliveries. And we wanted to ask, could we have almost like a check-in system near the restaurant so that they would only park so many vehicles there, and you wouldn't have crowding at those locations. I won't go into all of that. That seems kind of like way past us, in the past now, but at the time it did seem very important. But with doing that, we developed a simulator of the environment based on the real data from Grubhub. And we have expanded on that simulator and are thinking about ways that we can make it useful to the public so that others can test out different strategies. So here we looked at a number of different things. In addition to that, we've looked at a courier perspective. So not always thinking about the meal delivery systems perspective, but instead courier comes in and they want to make the most money for themselves. How do they position themselves? We've looked at evaluating the efficiency gains and risks of relying on an at-will workforce in this environment. Surge pricing to entice more at-will drivers during periods of high demand. That's a really big deal for the companies. They need to serve their clients, and when there's too much demand, they have a hard time attracting enough of the drivers. And then a green meal delivery problem. So I'll just touch on each of these briefly. I see the time. So the first one is this limited curbside pickup idea, where we had social distancing to increase safety and reduce traffic around the restaurants. We looked at postponing and bundling and putting Slack in to give more chances for bundling of these orders. The main thing we look at when we look at meal delivery is click to door time and maximum freshness. So click to door time is the time from when a person clicks on and wants the food until it arrives at their door. And maximum freshness is the time from when the restaurant has it ready until it arrives at your door. You want to minimize that so that the food is still hot, or cold, whatever it was supposed to be. We use simulation optimization in this approach. And develop that environment, and we have results that have to do with how often do we have violations and things like this. I'll skip forward. In the courier's perspective, we ask, well, what about this driver? The driver, should they drive around aimlessly when they're looking for a new job? Should they stay at their near their last delivery location? Should they hover near the restaurants? Should they position themselves between shopping centers and things like this? And we developed a simulation optimization and deep reinforcement learning approach for this. Now, we developed this DRL for the driver, him or herself, but realistically, a driver would not know how to use something like this. So we spent some time trying to investigate what the deep reinforcement learning method came up with as a solution to try to understand what kind of policy might be generated from the DRL's insights. So this is information about that deep reinforcement learning approach. We use two different approaches, a DQN and an actor-critic approach. Actor-critic approaches, for those of you not familiar with it, separate the and have two neural networks, one to look at the action set and one to look at the rewards that are received. Excuse me. And so ultimately, the goal of using a deep reinforcement learning approach is to overcome the curse of dimensionality that dynamic programs would offer. It's very hard to solve large-scale problems with that. They're also model-free, and we don't need to know the stochastic information. So here, we compared the results to results from a whole host of static policies and showed our dynamic policies and how much better they do. And you can see when there's sufficient orders or excess orders, the DRL does better than every policy we could think of. I think that's all I want to share with you on that. Okay, so then we asked about the workforce and whether or not it's okay to have a workforce that you can't totally rely on. And what's the risk of having this? And when you have a workforce that you can't rely on, excuse me one second, I need to.
While we're waiting, you guys out there might think about questions that we may want to ask in the upcoming Q&A section.
Yeah, I'm going to wrap up now. So I just have a tick. Okay, so the workforce, whether or not having an at-will workforce leads to risks to the company. And in fact, we developed, sophisticated methods for looking at both the ways of operating an at-will workforce or having a fixed workforce, and ultimately showed that there are real risks to working with the crowdsourced drivers and not having your own drivers at hand to do what you need. That should be considered. This last piece is about surge, about using actor-critic deep reinforcement learning approach for the surge situation and coming up with the surge pricing. And in meal delivery, in terms of having bicycles or cargo bikes doing some of that work to reduce the emissions. And what we did was we looked at different rates of penetration for the bicycles and found that if we have too much of our workforce at on the cargo bikes, they don't have as much reach. And in the US, they would not be able to serve the environment well. And so we found that there were risks to service with going with a larger percentage of the green delivery option. Last piece is just this idea of a same-day delivery problem. And I think I'll just wrap this up really quickly. We developed a novel way of thinking about the same-day delivery problem. The idea was that if I want something, I want it by the end of the day. So suppose I have an event I'm having at my house and I broke something. I broke my mixer. I really need that mixer. I don't have time to go shopping. I want it delivered today. If it's delivered tomorrow, it's too late. Or my son, this came up in my mind because my son had a book report due the next day and he needed the book and we had to have it by that day. Otherwise, it's too late. So the idea of same-day delivery, people are becoming more and more used to, at least in the US, getting same-day delivery, and they really want things delivered fast and, and they're willing to pay for it. And so we did some sophisticated models of this and asked, what time guarantee can we offer? And that's the decision variable. So different from other vehicle routing problems where you have a time window and you have to decide, who gets what when and how to, operate your system. We said, what time window can we offer them? And we want to think about long and short term obtaining the market. So we modeled this as a multi-stage stochastic mixed emitter program with two-stage programs in a rolling, shrinking horizon using a parallelized progressive hedging approach. And we applied this in the Arlington area and we compared it to different 2-hour, 3-hour, 4-hour policies and showed the benefits of the approach. We also showed that the company could trade off between getting an immediate cash flow so that they know they're going to get these people to push that final button and place that offer, because if you make a good time guarantee, they're more likely to buy, versus long-term sales volume that aligns with the changing business needs. So, depending on how much you want to offer, how aggressive you want to be, depends on what your company needs to be doing. So I will conclude now with some thoughts, taking all this back to the beginning questions that I've asked. So what is being shared? Is it really sharing, or is it an economic exchange? That's, one of our questions here. And so what are we sharing? Well, if we go to that stuff, so I talked about staff, stuff, and space. We think about the vehicle sharing. We're sharing the bicycles, we're sharing the cars, the excess capacity we have of these. So that's stuff. In ride sharing, we're doing the same thing. In parking, we're sharing space. And in delivery, we're really getting into that crowd sharing logistics. We're really sharing the staff. And so I like thinking about that. That's where we're coming from. We've shown that you can use all of these techniques that we've been using for many different things for the sharing economy, whether it's optimization and exact solution approaches, or different types of simulation or machine learning. These are all useful for these types of applications. And then I asked, well, what makes this new? I've talked about things that we've done recently, and I've talked about things we've done 20 years ago, 15 years ago. And what makes this new? Is it the application? Is it the scale at which we're doing these things? Is there something about the mechanism design that makes this new? I'm not sure. And are these new services, or really are they old services just repackaged? Are we really just calling, like today, the word equity is so big, and young people are saying, oh, everything has to be equitable, as if we didn't consider that, the well-being of people for decades. And so, are we just repackaging something we've all been thinking about a long time? I don't know the answer to these questions, but I think there's interesting to think about. The last thing I wrote is power change. Is it about who has the power now? And I really think that the digital economy has enabled individuals to act on their own account in ways that we've never been able to do before, or to join forces together to do so. So with that, I finished my talk. I will just share with you one slide, if it lets me. Oops. There's been a lot of papers, so they are on the slide. These are all from those works. And I just want to give a shout out. We have this journal from I4s that I am editor-in-chief of. It's a young journal. We love to get your papers. Think about us, sustainability analytics and modeling, using any kinds of operations research, mathematical modeling, any kind of quantitative techniques to take on global challenges and do good for the world. That's what this is about. And I thank a lot of people for their work on all of this work that I talked about. And you can find me at miller@gmu.edu if you want to reach out, and I'd be really excited to talk with people from here. And again, so sorry that I'm not there in person, and hoping to meet many of you in the coming days.
Fantastic, Elise. Thank you so much. And it's become evident how busy you are. It's lots of projects, and I think it was one of the most intense seminars that I've ever shared. So many thought-provoking ideas, so many projects in different areas, and I see we have quite a few questions already. We only have 10 minutes, so I may just go right into it and invite Mike Bell to unmute himself and ask his question on meal delivery, please.
Thank you, Rico, and thank you, Elise, for a fantastic talk that covered a vast area. My question relates particularly to your meal delivery work, and just to flag up that we've also been looking at the Grubhub data and looking at meal delivery, and also using a Markov model to represent the delivery activity. The aspect that we're actually looking at is more to do with the optimal locationing of ghost kitchens, given that you have a delivery system functioning underneath it.
Oh, that's kind of interesting. Yeah, I like that idea, because it's a whole new world in the way things are delivered. So why do we locate where we locate? It was for a totally different purpose. That's really interesting. I like that.
So that's my question is that, and you talked about labor and the worker side of things, and there is this transition, I think, away from gig economy workers being independent contractors to being employees. And I just wondered that if you've done anything on that and the implications of that for distribution activities.
So we have not looked at the labor issues other than this one paper where we looked at what are the pros and cons of having this other work, this kind of workforce, and what risks do you take on that you might not recognize, and what is that? How do we quantify those risks when you take on an at-will workforce? Because you gain from very efficient use of your workforce, but you lose from that they are not necessarily wanting to serve you unless they get what they want, right? So the margins are small, and so giving a lot of surge pricing can eat away all the benefit of offering the service, and so that's a risk to the operator. So we have not looked at other ways of thinking about the labor pool, and but I do think this is a really important area.
Thank you.
Agree with you. I do really like this idea that you have of stepping back and saying the world has changed. What would we do? How would we design it now? Not just live with what we did and now try to work with the best with it, right? So that's really interesting. I really like that.
Yeah, thank you.
Sandy, moving to parking and road pricing as it seems. Would you like to unmute yourself and ask a question, please?
Oh, sure. Thank you. Very interesting presentation, as the last person said. Lots of topics here. Just when you were talking about the parking thing, my thoughts immediately turned to other capacity issues around roads and whether your parking approach would apply equally to road pricing, or are you aware of similar approaches being used for road pricing?
That is such a good question. I imagine, you can apply this stuff generally to almost anything. One of the things about the parking is that there's parking owners, right? So there's a parking lot owner, another parking lot owner, or you as an individual own your own parking spot. So you're competing against each other. And in roadway pricing, I mean, maybe each different roadway, if they were competing with each other, could be different. Would have to be the different agents. So I think it's quite a different question. In the US, we have P3s, public-private partnerships, where we're operating more and more roadways that, that you get to choose whether or not to take. So I imagine there's something there. I think you're onto something, but I don't think we could take what we did and apply it directly.
Thank you.
Mikhail.
Yes, hi Elise, thank you very much. Your algorithm and your problem formulation that you showed about the meal delivery, could you formulate something almost identical for the crowdsourced parcel delivery? Because it sounds very similar. Picking something up, it's not food, it's a parcel. Or is it slightly different? Because parcel deliveries is usually a centralized origin, and if you have parcel lockers, there's also to some extent centralized destination. So maybe instead of a many-to-many, you get a few-to-few problem. So maybe it's even simpler. I'm just trying to find out, is it a similar problem or not?
So two things that I'll think there. One is the meal delivery problem is a little different from parcel delivery in that you've got customers, restaurants, and the restaurants have a whole lot going on at them. And then you have the end delivery back to the customer, right? So there's these three players. There's the meal delivery environment that's trying to figure out how to give this out. There's the customer who has to make the order, and there's the restaurant that plays this middle role. That's different than the pickup locations, I think. I don't think it's the same exact problem. I could be wrong, though. I have to think more about that. We, in the parcel area, the last problem that I rushed through, the same day delivery problem, that was for parcels. And I'm trying to think what makes it different. Well, I don't know. I think there's different aspects to these problems. So the restaurants, you it's not the same restaurant, you know what I mean? So that they're not, it's not like one company that has a bunch of different depots and you can go to any depot. Each restaurant has its different things. So when you try to cluster things, you might have somebody going to this restaurant and it has a time window for pickup. That's very, very important. That time when you go to the restaurant is critical for keeping that food hot and fresh, which I don't think has any bearing in the parcel delivery. So I don't know, we treated them very differently. And I think there's some significant differences with the restaurant aspect.
Yeah, I think it's much simpler. The parcel delivery is probably much simpler with no time pressure and centralized.
And your goal is different. You don't worry about click to door times or freshness. You definitely worry more about consolidation. You're going to consolidate more. So our answers look different in the two different worlds. So the last problem that I showed you, the same day delivery problem, we modeled as a more traditional, vehicle routing kind of, it's not really a vehicle routing problem. It's more of a, it's a pricing problem, but it has this aspect of, I want to try to collapse these things together to have efficiencies in my deliveries. Otherwise, things get too expensive and I can't make a good offer. And my time guarantee, and then there's trade-off with time guarantee. So you have to have a reasonably efficient system compared to, the services you want to offer that are so good that will keep them buying and get them to make that final click and push the actual, here's my credit card information button. So I think they're quite different.
Thank you.
I think we have time for a final question. Francesco was first. So Francesco, please. And John, should we find a way to have your question answered either later today or tomorrow?
Yeah, sure. I have to be selective in the questions. And first of all, I'd like to echo Mike's words. It's an impressive set of applications and methodologies that you have presented. And I know that you have even been selective in choosing some topics that you're covering, since I've also heard your keynote in June at ART, and there were even more applications and methodologies. So yeah, I actually wanted to have a small discussion on your first definition on shared economy, and in particular, when you were using the word excess capacity.
Yeah.
Because, I mean, as an optimizer, I think it would be important to start with the input of excess capacity. So first of all, what is excess capacity in reality? How to quantify it? And then do you actually, is there also an induced excess capacity in reality? People may, for some business models, realize that they may have an opportunity to, get rid of maybe some of their own utilization of their own car, because maybe it's more profitable to give it shared. So how to actually define the boundary and let's say quantify it in a clear way, this excess capacity term, this excess capacity quantity?
I love this question. Since I was sick with COVID last week, I watched a lot of TV here, and I watched this one show where they, redo some house or whatever, and they were redoing the house to be a vacation house that other people are going to rent. So instead of it being their excess capacity, they turned it into a business. And I think this is really the truth, that people are, it may have started as sharing. It may have started as a way of maybe making a little extra money off of what you have that other people need because there's not enough to go around of whatever it is. But it's turning more and more into a business. And now we're really thinking about how to make money out of it. And I think we always come back to the same thing.
I think here in Sydney, this is even going into an extreme. I mean, having the experience now of looking for apartments for a short stay and then seeing how expensive it can be to rent this apartment, I could also imagine residents of this city to maybe even pay their own vacations by renting their house. So they may, at a certain point, have extra vacation just because they could earn more money
Right.
with their house. And this, reflected into the mobility, it might be an extreme when we are also trading mobility options. And then maybe we could get into a situation where we buy a car, knowing the fact that if we share it, it might pay back and even become a source of income for us. It's really an unexplored field here.
I think you are so right. And this even comes back to this question, what is the sharing economy? Is this really sharing? I think it's really an economic exchange, and we're just figuring out how to exploit the digital economy.
Yeah.
But in some ways, this idea that, okay, we don't have enough of these things to go around, and we're now able to do these things. We're able to allow people to take our places and you don't have to go to a hotel anymore. That you're able to rent out, like the idea of having a new market for putting your own, parking lot, parking spot in your building. So maybe you're right. Maybe your building lets you rent it for $400 a month. But then you can rent it out per day for $50 and you make it back in no time at all. You've turned it into a business. That might be true, but it's still one less space that we have to build, one less little spot of concrete or whatever it is we'll do to the earth. So we have that much more breathing area. So there's still some benefit, I think, that comes from this, but people are learning how to maximize their own benefit.
Yeah. But it's a good message that there must be somebody that should in some way give a cap or regulate it. Otherwise, we may get into the wild. But I think we can continue these. I'm taking the time of other questions, and I'd love to continue talking to you offline.
And I'm hopeful that Elise, as she indicated already, that she will be available for further questions and meetings later in the week, which is fantastic. Unfortunately, we need to sort of conclude here the seminar, because already slightly over time. And I would like to invite everyone to join me in congratulating and thanking Elise to this fantastic seminar in the usual way. So we usually clap when we are face to face. But
thank you all.
Well done, despite all the COVID hiccups and all that. It was really fascinating, and I look forward to seeing you face to face later in the week. That leaves me with just one thing to do, and that is to invite everyone to our next ITLS Leadership and Policy seminar, which will be next Tuesday at noon again, where we will welcome Professor Kai Hobeck from Kuhn Logistics University in Hamburg, and he will talk to us about human-machine interaction and demand forecasting. So please do join us again next week, and then in following weeks we have a packed program. And thank you again for your attention today, and thank you, Elise, for this fantastic seminar. Thank you, everyone.
Thank you all. I really, really enjoy getting to know you, even if it's only remotely.